Like I said, I guess we'll just use this time to kind of finish up this chapter here. Just a few more slides to go. And again, if you do think about any type of questions that you might have, just let me know when we are done here. So we're going to finish up talking about a few different sort of properties of solutions. We've talked about now concentrations of solutions, how to do dilutions, involving solutions. So some properties of solutions, for example, we do have something that's referred to as a semi-pyramidal membrane, and that allows solvent molecules such as water and small particles to kind of pass through, and other things are sort of excluded. So you can kind of think of the membrane, as sort of having holes in it, if you will. And there's certain size guys which are small enough to sort of pass through the hole, but there are certain ones that will be a little bit too big to sort of get through the hole and will be sort of trapped by this membrane. So there's different ways we sort of describe certain things. There are things that are known as colloids. Colloids are much larger than solute particles in solution. They're large molecules like proteins or groups of molecules. They are homogeneous, which means they are the same throughout. So they are mixtures, kind of like solutions almost. They don't look like different layers. They're small enough to pass through filters, like a piece of filter paper, but they're too large to kind of pass through the semi-pyramidal membranes. There's suspensions. Suspensions are heterogeneous, and that much like a heterogeneous mixture, you see different parts as not all looking the same throughout. They're often very large that you can see them with your naked eye. These are pretty much so large that they get trapped by filter paper. They get trapped by semi-pyramidal membranes. They're really just kind of too big to go through a lot of things. So we kind of look at some differences here. Solutions are circles, colloids are triangles, and our suspensions there are the squares in this example. And we do see that our suspensions sort of settle out of solution. Our solution and colloids are kind of moving around. If we pour all those guys through a piece of filter paper, we see that the suspensions get caught there, while the solution and the colloids are able to pass through like a filter paper on a funnel. And if we take it into a membrane here, we can see that the solutions are small enough to really pass through this membrane, again, trapping both the kind of larger particles like colloids and also suspensions. So suspension is something you can really see with your naked eye. Definitely gets trapped everywhere. A colloid doesn't get trapped on filter paper, but does get trapped in a semi-pyramidal membrane and more of a homogeneous type of situation there. That brings us to osmosis and dialysis. Let's first talk about what osmosis is. Osmosis is the sort of natural process where solvent water molecules basically move from areas of lower concentration to areas of higher concentration. So the idea here is it wants to sort of dilute down the more concentrated side to kind of bring the concentration a little bit equal. So for example, if we had sort of a tube and this tube was separated by a semi-pyramidal membrane, so we'll circle that since it's right there. So if we have this semi-pyramidal membrane that separates it out, and on one side we have just plain old water, on the other side we have something like salt water. Salt water would be more concentrated because it has something like sodium chloride dissolved in it than just pure water, which has nothing dissolved in it. So what's going to happen is the process of osmosis will occur, and the water molecules on the left-hand side of that membrane will go, we need to start flowing this way in an effort to kind of dilute down the salt water. And it will continue to flow this way until it basically reaches what is referred to as the osmotic pressure. And that will basically stop the flow, the osmotic pressure of these water molecules to the other side. And the effort here would be for it to basically sort of dilute it. Now, pure water has no osmotic pressure because it basically has nothing dissolved in it. And one way we sort of can measure osmotic pressure, or sort of, the concentration of it, if you will, is through a concentration which is sometimes referred to as I'm just writing all over the place here. Something that is referred to as osmolarity. So osmolarity is basically I times the molarity. And that is basically what is sometimes referred to as the osmolarity of it. Osmoles before liters. What does the I represent? Well, the I represents really the number of particles that are in the solution. So really, osmotic pressure and the pressure exerted by a solution has a lot to do with basically how many sort of particles are floating around that solution. The more particles, the more sort of osmotic pressure basically will be. So for example, if we had a 1 molar sodium chloride solution, when we talk sodium chloride, it will break apart into, as we talked about, Na plus and Cl minus. That is a grand total of 1 and 2 ions, which means the I value here would equal 2 in this case. And again, it's basically just the number of particles or ions that are present. And that means that if we wanted to calculate the osmolarity of it, which is sometimes referred to as osmol, we would take 2, which is the I value, times the molarity, which is 1 molar, and we would end up with 2 osmolarity as our sort of osmotic pressure concentration. Now, is there a big difference between a 1 molar sodium chloride solution versus a 1 molar calcium chloride solution? Well, when we have calcium chloride, it breaks apart into a calcium ion and 2 chloride ions. If we add up all the ions that are present, that's 2 for the chloride, 1 for the calcium, which means in this case, I would equal 3. 1 calcium, 2 chloride ions, which means if we calculate the osmolarity of our calcium chloride solution, it would be 3 times 1 molar, which would give me 3 osmolarity. We would expect this guy to have a greater osmotic pressure than the sodium chloride. Again, it's related to how much particles are floating around in that particular solution. Water has no osmotic pressure because in pure water, you have nothing else dissolved in there. There's no ions, there's no particles, it's just water. And it has an osmotic pressure of 0 in this case. Any questions on that there? Now, you maybe have heard of reverse osmosis. And reverse osmosis is when you basically apply a pressure greater than the atmospheric pressure. So this atmospheric pressure stops the flow of water molecules. So if you apply a pressure that's greater than the osmotic pressure, what you're going to basically do is force everything back the other way. And what you'll do in that case is force everything, the water, the salt, and everything back the other way. And if you set up a bunch of really good filters here, if you will, you can pretty much trap all the stuff that you don't want, and you'll end up with just pure water on the other side. So reverse osmosis is when we apply a pressure greater than or equal to the atmospheric pressure back down on it, and that allows everything to be pushed basically the other way. Which again, if you sort of filter out a lot of stuff, that will prevent, particles from being in there, and you'll get just pure water. Here's a prettier picture of what I was drawing, but here's our osmotic pressure again. At some point, the flow of water molecules will be stopped by the atmospheric pressure pushing back down on it. And that, again, is what is osmotic pressure. There's also a few different ways that you can describe certain solutions. There is isotonic, hypotonic, and hypertonic solutions. Isotonic solutions exert the same osmotic pressure as body fluids. So most IV solutions are isotonic. So what does that mean? Well, isotonic means basically that if we take the classic example of a red blood cell and we put it into a isotonic solution, basically the blood cell would act as a membrane and water would flow in and out basically of the cell at the same rate, which means nothing bad's going to really happen to it. It should be okay. What is considered an isotonic solution? Considered an isotonic solution is if you have a solution that is 0.9% by mass, (0.9% sodium chloride by mass, so volume. That is sometimes also referred to as a saline solution. Doesn't necessarily have to be sodium chloride. It could be like potassium chloride, some type of ionic compound, but 0.9% is the key there. And also 5% glucose is considered isotonic. So if you have a 5% glucose solution, if you have a 0.9% sodium chloride type solution, those are considered isotonic solutions. That means if you had something like a red blood cell acting as a membrane, you would expect equal flow in and out of the cell, which is actually a good thing. Obviously, if they're giving you an IV bag, you're in some type of trouble there probably. So you don't want to give something that's going to basically screw up the osmotic pressure of your cells and cause them to either shrink or swell, which obviously would not be good situations. And that is the situations that occur in a hypotonic solution. So hypo means less than. So it means lower than or less than. So basically what happens is if we put that same sort of red blood cell acting as sort of a membrane into a hypotonic solution, that means that outside of the cell is less concentrated than inside the cell. So outside of the cell is less concentrated than inside of the cell. So what's going to happen is by osmosis, everybody from outside the cell is going to go, we need to rush into the cell because we need to dilute it down. The result of that is our cell is going to start to swell from all that and burst, which is not a good thing. That's known as hemolysis. Again, not really a good idea in that case, or a good thing that occurs. So what happens in sort of the other situation if we actually have a hypertonic solution? Hyper means more than, which means outside the cell, the solution is greater than inside of the cell. So again, if we look at sort of a drawing of our red blood cell in a hypertonic solution, that again means outside the cell is actually more concentrated than inside the cell. So in this particular case, what's going to happen is the red blood cell is going to go, I need to do some osmosis here. I need to release all my water from my cell to the outside in an effort to try to dilute the outside. The result of that is we're going to get a cell that will start to shrink and go through what is referred to as crenation, which is not a good thing. And again, that would cause some problems there. Any questions on those sort of three types of solutions? Okay, let's take a look at a couple examples, maybe. Let's take a look at, let's say we put a red blood cell into each of the following solutions. What would happen? Is it a hypertonic solution? Is it isotonic? Is it hypotonic? And what will happen to the red blood cell? Will it shrink? Will it swell? Will it be okay? So let's say we put the red blood cell in a 7% sodium chloride solution. Let's say we put the red blood cell in a 4% glucose solution. Let's say we put it into a 0.9% sodium chloride solution. Let's say we put it into pure water. And let's say we put it into a 9% glucose solution. All right, so for each of them, decide, are these solutions hypertonic, isotonic, or hypertonic? And what will happen? Will our guy shrink? Will he swell? Will he go through crenation or hemolysis, right? All right, take a couple of minutes to see what you come up with here. To do this, it's a good idea to keep in mind what we talked about, that basically an isotonic solution is 0.9% sodium chloride, or an ionic type compound, or saline solution, or a 5% glucose. So those are really obviously important numbers, as it will allow you to answer questions like these. So when we look at 7% sodium chloride, it's as simple as 7% is a larger number than 0.9. So a larger number would imply that this should be a hypertonic, tonic solution. And what that means again is that outside the cell is more concentrated than inside the cell, which means, excuse me, which means we would expect basically the cell to go through osmosis and try to dilute the outside. The result of that is we should see the cell start to shrink, which is the process of crenation. Any questions on that particular one there? Let's go with 4% glucose. So glucose, our isotonic is 5%. So 4% is less than 5, which means less than means it is hypotonic. Again, what that means is in this particular case, outside the cell is actually less concentrated than inside the cell. So again, osmosis means it wants to go from a lower concentration to a higher concentration, which means we will get everybody from outside the cell here basically to flow into it. As it's flowing into it, that should then make it start to swell, which is the process known as hemolysis. Again, not a good situation in that case. Any questions on that one? 0.9% sodium chloride is, as we see here, exactly an isotonic solution. So this means it's an isotonic solution. This also would then mean that the cell will be okay, because in an isotonic solution, we would have equal flow in and out of the cell. And thus the cell obviously won't shrink, it won't swell. So it won't shrink, it won't swell, it won't burst or anything like that. So everything will be okay in that particular case. We have a 9% glucose. So 9 is obviously greater than 5, which means this is a hypertonic solution. Hypertonic means greater than. So again, that means outside is greater than, which is this situation here, hyper. That again means that the cell will try to basically dilute down the outside, and we would expect to see the cell start to shrink and go through crenation. Lastly, here we have pure water. And pure water is an interesting one because people go, it's water, so can't really hurt. In this particular case, it can hurt. Water has no osmotic pressure, which means it would then fall in the hypotonic situation. So this would actually be hypotonic, which means outside is less concentrated than inside, and we will get everybody rushing in this case. The cell will fill up with water, it will start to swell, and it will burst, which is known as hemolysis. Any question on the different types of solutions, how to determine isotonic, hypertonic, and hypotonic? Obviously, this table sort of describes everything we talked about. The osmolarity related to body fluids is equal in isotonic, greater than in hyper, and less than in hypo. And the effect on the cell, again, in an isotonic, we got water flowing in and out of the cell at an equal rate, so nothing bad happens to it. In terms of hypertonic, because it's more concentrated, on the outside, we get water basically running out of the cell, and that's again why it starts to shrink, and vice versa. In the hypotonic, we get the net water rushing into the cell because the cell is more concentrated than the outside solution. And here's again some pictures that illustrate that. Here, isotonic solution. We have a nice donut. Hypertonic solution, everybody's rushing in until it bursts. Jelly donut. Hypertonic solution, we got everybody rushing out in the hypertonic solution, so it shrinks donut hole in this case, as the guy looks like that. Any questions on those type of solutions? Okay. Here's just a table of some of the stuff we talked about. We didn't talk about any of these things, but we did talk about sort of these guys here, I believe. A little bit. All right, so lastly here, dialysis is a process that's very similar to osmosis. Oftentimes you can use something like a dialysis bag. For example, maybe the experiment this week or something like that might do that. The bag itself has little sort of holes that you can't really visually see yourself. Again, it's kind of like what we talked about earlier, sort of the size is what excludes things from passing through, say, a dialysis bag. Again, something too large will kind of get stuck as it tries to move through that hole. Something small enough is able to pass through the actual hole. And sometimes, you know, we'll can use something like a dialysis bag to sort of equilibrate something in the lab. Maybe we want it in a particular environment. You could put like a protein, for example, in a bag, kind of put it into a solution that's the same environment as maybe in the body, and leave it sit in there to really equilibrate and be very much like it would be, say, in the body. And I think there's a lab where you kind of do this. You put a whole bunch of stuff into a dialysis bag, and every so often you sort of test the outside solution to kind of see what is in the outside solution. And obviously, if it's in the outside solution, that meant it was able to travel out of the dialysis bag. If you don't find it in the outside solution, that means it's still in the dialysis bag. And you continue that process for a while. Again, certain size molecules will be too large really to pass through. Other ones are small enough that they can pass through. And for example, in that experiment, at some point, I think at the end, you like pop the bag open to kind of see what is still kind of trapped inside the bag. We also use something like this, in our body, kidneys and so forth, to remove certain waste products from our body, sort of filter out sort of these things. And obviously, if you have a problem with that process, you sometimes do need to go through dialysis to help your body really kind of filter out these things that sometimes are naturally sort of filtered out, and you might need some help to do that. Any questions on any of that stuff there?